Hello, physics folks. Just doing a screencast here on sound. This week we will be dealing with sound. That is chapter 26 in the book. So I'll put a PDF copy of the book in there for you so you can look up answers as needed. Make sure you look through the chapter. I'm going to try an Edpuzzle, my first attempt at this. So hopefully you guys can watch the video within and answer the questions throughout. The rest of the week's homework will all have to do with sound. There will be some quick questions to answer every night. And I'll do 2 hangouts this week. I'll do one on Monday and Thursday. Okay, so hope to see you then. And here we go. Sound. So remember, transverse waves, as you can see in the picture, that's what a transverse wave looks like. This is a little bit of review, by the way. These first few slides you have seen before. Motion is at a right angle to the direction the wave is moving. Remember that when the motion of the medium is at right angles to the direction in which the wave travels. So notice in the picture here, you have the right angles, okay? That's relative to the medium. Example, rope shaking up and down. Longitudinal waves. Remember longitudinal wave? If particles oscillate parallel along the direction of the wave. So opposite of the right angles would be the parallel. That would be your longitudinal right here. Okay. Sound moves compressions of air parallel to the source. So sound is a longitudinal wave. A standing waves is a wave that appears to stay in one place. It does not seem to move through the medium. The incident and reflective waves interfere to produce a standing wave. The nodes are places that remain stationary. So as you can see here, these would be the nodes all along here where the wave is stationary. Okay. Remember the fire engine? Remember the sound? Remember the whee as the sound changes from when it comes to you versus when it leaves. Remember the pitch changes. Remember we talked about bow waves. By the way, that was the Doppler effect. You forgot that. Bow waves. Remember we talked about bow waves. If the bug goes faster than the wave speed, it produces wave crests. The crests overlap at the edges, creating a V shape called a bow wave. The bow wave appears to be dragging behind the bug. This is similar to the waves one may see trailing a speedboat. The wavelength is 1 meter, and the wavelength per second passes the pole, then the speed of the wave is 1 meter a second. Where V is wave speed, lambda is wavelength, and F is wave frequency. So remember that formula. That formula will come up again this week. Same formula. Recall the math of the formula, how we use that, just like the triangle we've seen before. Wave speed, meters a second, that's your V. Frequency is in hertz, that's your F. And lambda, that's the Greek symbol for wavelength, that's in meters. Here's some review of some of the math that we've done in the past. Notice in the first one, you needed to find the frequency, so you needed to divide the number of waves divided by the seconds to find it, and that was 0.05 hertz. The second one, you needed to multiply to find the speed, that's the V times H, or lambda, sorry. That was 1.5 meters a second. And the last one, we needed to find out if the amplitude of the wave change does the speed. No, the amplitude only affects the energy of the wave. Sound, here we go. Source of the sound. All sounds originate in vibrations of material objects. Sends disturbance through a surrounding medium, air in the form of longitudinal waves. Frequency of the sound waves equals the frequency of the vibrating source. Oh, by the way, those fun tuning forks, if we ever go to school again, well, actually, we'll be going next year. We'll have to show you some of these forks. You'll have to come in and check them out. Maybe I can somehow figure out a lab to do online with you so you just can see some of these forks and how they work in relation to the sound waves. This is usually part of the class where we do a tuning fork sound lab. Pitch. What is pitch? Pitch is a description of our subjective impression about the frequency of sound. So how things sound, their pitch. Is it high pitch? Ah. Is it low? Oh. High pitched sound, like that form a piccolo has a high, or piccolo, sorry. Piccolo has a high vibration frequency. A low pitched sound, like that from a foghorn, has a low vibration frequency. A young person can normally hear pitches with frequencies from about 20 to 20,000 hertz. As we grow older, our hearing range shrinks, especially at the high frequency end. So there are sounds that are targeted for you teenagers that I can't hear. We have gone into stores where they don't want teenagers loitering around, and my daughter is freaking out. Her ears are killing her, and I don't know why, because I can't hear what she hears, because I don't hear those high frequency pitches like you all do. Also notice the ages here. Age is on the side for men, 15 to 65. Notice that it drops dramatically. What we can hear, that's in men, that's in women. So as you see here, the women tend to hear things better. So yes, it is true that women hear better. You can see right here on the graph. Hearing loss in decibels, that's on this side here, and this is in the frequency in hertz. So how did I lose my hearing? How did it get worse over the years? Probably for me would be all the concerts that I attended. All the music concerts over the years probably did a number on my hearing. Sound waves with frequencies below 20 hertz are called infrasonic. Sound waves with frequency above 20,000 hertz are called ultrasonic. Dogs can hear frequency of 40,000 hertz. So this is why dogs really freak out when it comes to loud noises, fireworks, loud booms, gunshots. It really bothers them worse than us. Bats can hear sounds at over 100,000 hertz. Okay, so I believe that's where I wanted to end things today. See you tomorrow. Goodbye.